Anyone hear me?
Can hear you.
Thank you. All right. I'd like to spend today's lecture talking about threads and how XV6 does thread switching. This is sort of one of our under the hood lectures about XV6. We've had lectures before about how system calls, interrupts, page tables, and locks work. Today we're going to talk about how it is that XV6 switches among different processes. Now, the reason for this, the highest level reason for this, is that people like their computer to be able to do more than one task at the same time. So the reason might be that you're supporting time sharing, like Athena allows many users to log in at the same time, and they can all run processes, or even on a single user machine, or even your iPhone. You may run many different processes and expect the computer to do all the things you ask of it, not just one thing. Another reason that people like to support multiple tasks is because it can ease program structure. Threads in particular, today's topic, are sometimes used as a way to help programmers put together a program in a sort of simple, elegant way to reduce complexity. And you actually saw an example of this in the first lab with the prime number sieve, which didn't use threads exactly, but used multiple processes in order to help structure your prime number sieve software. And arguably, it's sort of a more convenient or elegant or simpler way to write that software. And a final reason why people use threads is to get parallel speed up from multi-core machines. So it's common to break up your program in a way that using threads to allow different parts of the same program to run on different cores. And if you can, maybe if you're lucky, if you can split your program up to run on 4 threads on 4 cores, you might be able to get a factor of 4 speed up in how fast it runs. And indeed, you can view the XV6 kernel as a multi-core parallel program. So what threads are is an abstraction to simplify programming when you have many tasks, when you want to juggle many tasks. So what a thread is you can think of a thread as just being a single serial execution. If you just write a program that does one thing after another and you run that program, you can view the program as a sort of single thread of control. So, and this is a loose definition because there's many different sort of flavors of what people mean by threads, but we'll say it's one serial execution. So it's what you get if you fire up one CPU and have it, just execute one instruction after another in the ordinary way. We often talk about a thread having state because it's going to turn out we're going to want to save away a thread state and restore it later. And so the right way to think about a thread state, for the most part, the most important part perhaps of the thread state is its program counter. Because it's an execution, we care a lot about where is it in its execution and what address is it executing instructions. But also, we care about the rest of the microprocessor state that's required to support this execution. And so that means it's the state of a thread includes the registers that the compiler uses to hold variables. It also, because just the way the compiler generates code, a thread state includes a stack. So typically, each thread has its own stack dedicated to executing that thread, and the stack records the record of function calls that reflect the current point in the execution of that thread. And so what a threading system, XV6 includes a threading system inside it. What a threading system does is manage automate the interleaving of multiple threads. We'd like to be able to fire up 2 or 4 or 100 or 1,000 threads and have the threading system figure out how to juggle all those threads and cause them all to make progress and all to execute. And there's really 2 main strategies. So we want to interleave. This is going to be a big topic here, is how to interleave threads, many threads. One way to interleave the execution of many threads is to have multiple CPUs, maybe as on a multi-core processor. And then each CPU can run its own thread. So if you have 4 CPUs, there's an obvious way to run, so 4 threads is to run 1 thread per CPU. And then each thread automatically gets its own program counter and registers. That is, the program counter and registers associated with the CPU it's running on. But if you have 4 CPUs and you have 1,000 threads, then using 1 core per thread is not going to be enough of an answer. And so the other main strategy that we'll see, indeed the topic of most of this lecture, is how each CPU is going to switch among different threads. So if I have 1 CPU and 1,000 threads, we're gonna see how XV6 builds a switching system that allows XV6 to run 1 thread for a while and then switch and set aside and save the state of that 1 thread and switch to executing a 2nd thread for a while and then a 3rd thread and so forth until it's executed a little bit of each thread and then go back and execute more of the 1st thread and so on. And indeed, with XV6, like most operating systems, combines these. XV6 will run threads on all the cores that are available, and each core will switch among threads. Because there's typically, although not always, there's typically many more threads than there are CPUs. One of the many ways in which different threading systems or instances of threading systems differ is in whether or not they share memory. And so this is a important point. One possibility is that you could have a single address space with many threads executing in that address space, and then they see each other's changes. If one of the threads sharing some memory modifies a variable, then the other thread sharing that memory will see the modification. And so it's in the context of threads running and sharing memory that we need things like the locks that you saw in the last lecture. XV6 kernel is shared memory. So XV6, XV6 supports the notion of kernel threads. There's 1 kernel thread per process that executes system calls for that process. All those kernel threads share kernel memory. So XV6 kernel threads do share memory. On the other hand, XV6 has another kind of threads. Each user process essentially has a single thread of control that executes the user instructions for that process. And indeed, a lot of the XV6 kernel threading machinery is ultimately in support of being able to support and switch among many user processes. Each user process has some memory and a single thread that runs in that memory. So XV6 user processes each process has 1 thread, and so there's no sharing of memory among threads within a single XV6 user process. Of course, you can have multiple processes, but each of those processes is an address space with a single thread. The processes in XV6 don't share memory. In other more sophisticated operating systems, for example, Linux, Linux at user level does allow multiple threads in a process, and those threads share the memory of that single process. And that's super cool if you want to write user level programs that user level parallel programs that get speed up from multiple cores. But it requires sort of it uses a lot of the same basic techniques we're going to talk about today, but there's a certain amount more sophistication in Linux to get it to keep track of multiple threads per process instead of just 1. Okay, at a sort of high level, I just want to mention that there's other ways to support the interleaving of multiple tasks on a single computer. And we're not going to talk about them, but if you're curious, you can look up things like event-driven programming or state machines. And these are non-thread techniques to share 1 computer among many different tasks. It turns out, and sort of on the spectrum of different schemes for supporting multiple tasks on a computer, threads are not very efficient. There's other more efficient schemes, but threads are usually the most convenient way, the most programmer-friendly way to support lots of sort of different tasks. Okay, there's a couple of challenges that we're going to have to bite off if we want to implement a threading system. So this is just high-level challenges. One is, as I mentioned before, how to actually implement the switching for interleave, the switching that allows us to interleave the execution of multiple threads. And this sort of broad name for this process of switching, deciding, oh, I'm going to leave off one thread and start executing another thread, it's often called scheduling. And we'll see that XV6 indeed has an actual piece of code that's the scheduler. Indeed, it has multiple schedulers, one per core. But the general idea of how do you drive the decision to switch from one to another, how to pick the next thread to run, is called scheduling. Another question is, if you want to actually implement the switch from one thread to another, you need to save and restore. So we need to decide what needs to be saved, and where to save it. What needs to be saved when we leave off executing one thread, and restored when we want to resume executing that thread at some later time. And the final question is what to do about compute-bound threads. Many of the options, many of the most straightforward options for thread switching involve the thread sort of voluntarily saying, well, I'm going to save away my state and sort of run another, let another thread be run. But what if we have a user program that's, doing some long running calculation that might take hours? It's not going to be particularly thinking about, oh, now would be good time to let something else run. So it's most convenient to have some way of just sort of automatically revoking control from some long running compute bound process, setting it aside and maybe running it later. All right, so I'm going to talk about these. I'm actually going to talk about the machinery for dealing with compute bound threads first. And the scheme for that is something you've come up before, and that's timer interrupts. And the idea here is that there's a little piece of hardware on each CPU, on each core, that generates periodic interrupts. And the XV6 or any operating system really arranges to have those interrupts delivered to the kernel. So even if we're running at user level in some loop that's computing the first billion digits of pi, nevertheless, the timer interrupt is going to go off at some point, maybe every 10 milliseconds, and transfer control from that user level code into the interrupt handler in the kernel. And so that's the sort of first step in the kernel being able to gain control to switch among different user level processes, or user level threads, even if those user level threads aren't cooperative. And the basic scheme is that in the interrupt handler, so we're going to have a kernel handler for these interrupts, and we'll see that the kernel handler yields. This is the sort of usual name for this. It yields, the kernel handler sort of voluntarily yields the CPU back to the scheduler and tells the scheduler, look, you can let something else run now. And this yielding is really a form of thread switch that saves away the state of the current thread, and so it can be restored later. As we'll see, the full story here, actually you've seen a lot of the full story here because it involves an interrupt, which you already know about. The full story is somewhat complex, but the basic idea is that a timer interrupt gives control to the kernel, and the kernel voluntarily yields the CPU. This is called, as a piece of terminology, preemptive scheduling. And what that means is that, what the preemptive means is that even if the code that's running doesn't want to, doesn't explicitly yield the CPU, the timer interrupt is going to take control away, and we're going to yield for it. And the opposite of preemptive scheduling might be called maybe voluntary scheduling. And the interesting thing is that the implementation in XV6 and other operating systems of preemptive scheduling is this timer interrupt, which forcibly takes away the CPU. And then the kernel basically does a voluntary yield or thread switch on behalf of that process. Another just piece of terminology that comes up here is that while a thread's running, we need to distinguish, the system needs to distinguish between threads that are currently actually running on some CPU versus threads that would like to run but aren't currently running on any CPU, but could run if a CPU became free, versus threads that actually don't want to run because they're waiting for I/O or waiting for some event. And unfortunately, this distinction is often called state, even though the full state of a thread is actually much more complicated than that. Since this is going to come up, I just want to list out a couple of states that we'll be seeing. And these are states that XV6 actually maintains. There's a state called running, which means it's actually executing on some CPU right now. There's runnable, which means not currently executing anywhere, and just a saved state, but would like to run as soon as possible. And then it turns out there's a state which won't come out much today, but will come up next week, called sleeping, which means the thread's waiting for some I/O event and only wants to run after the I/O event occurs. So today we're mostly concerned with running and runnable threads. And what this preemptive switch does, what this timer interrupt does, and the yield is basically convert a running thread, whatever thread was interrupted by the timer, into a runnable thread. That is the thread that's, by yielding, you're converting that thread into a thread that's not running right now, but would actually like to, clearly, because it was running at the time of the timer interrupt. Okay, so a running thread, its program counter and registers are actually in the CPU, in the hardware registers of the CPU that's executing it. A runnable thread, though, has no, doesn't have a CPU associated with it, and therefore we need to save, for every runnable state, we need to save whatever CPU state, whatever state the CPU was keeping when that thread was running. So we need to copy the CPU contents, which is not RAM, but just registers really, from the CPU into memory somewhere to save them when we turn a thread from running to runnable. And again, this is basically the state we have to explicitly save here is just the state, the executing state in the CPU, which is the program counter and the registers in the CPU. So these need to be saved when we convert a thread to runnable. When some scheduler finally decides to run a runnable thread, then as part of the many steps in getting that thread going again and resuming it, we're going to see that the saved program counter registers are copied back into the CPU's actual register on the CPU that the scheduler decides to run it on. All right. Any questions about this terminology? All right, I'm going to now sort of talk about a sort of more XV6 oriented view of things. I'm going to draw two pictures really of threads in XV6, a kind of simplified picture and a more detailed picture. So as usual, we have the user stuff up here and the kernel down here. We might be running multiple processes at user level, maybe the C compiler and the LS and a shell. They may or may not be all wanting to run at the same time. At user level, each of these processes has it has memory, and of particular interest to us, each of these processes has a user stack, and while it's running, it has registers in the RISC-V hardware, so PC plus registers. right? So while the program is running, you know, there's essentially a thread of control that's running up at user level. And the way I'm going to talk about it is as if there's a user thread that consists of the user stack, user memory, user program counter, user registers. If the program makes a system call or is interrupted and goes into the kernel, then this stuff's saved away in this program's trap frame, and the kernel thread for this program is activated. And so this is the trap frame holds saved user stuff. After we saved away the user piece, program counter and registers, then we switch the CPU to using the kernel stack. And you know, we don't need to restore registers because the kernel thread for a process isn't really running and has no real save state when the user thread is running. Instead, it's sort of the kernel thread is kind of activated on its stack the first time in the trampoline and user trap code. And then the kernel runs for a while, maybe running a system call or an interrupt handler or whatever it may be. And sometimes, if it's a system call in particular, we'll just simply return from this point back to the same process, and the return to user space will restore this program's program counter and registers. But it could also be that instead of simply returning for one reason or another, maybe because it was a timer interrupt, we're actually going to switch to another process. And the very high level view of that is that if the x86 scheduler decides to switch from this process to a different process, the first thing that really happens is that we're going to switch kernel threads from this process's kernel thread to the other process's kernel thread. And then the other process's kernel thread will turn back to user space. So supposing that the C compiler, say, needs to read the disk, and so it's going to yield the CPU while it's sleeping to wait for the disk read to complete. And maybe LS wants to execute and is in runnable state. What the x86 scheduler may do is that, well, if LS is in runnable state, that means it left off somewhere and its state was saved away, possibly by a timer interrupt. And so the LS will actually have a saved trap frame with user registers and its own kernel stack. And as it turns out, a saved set of kernel registers associated with the kernel thread, which is going to be called the context. So if x86 switches from the compiler kernel thread to LS's kernel thread, x86 will save away the kernel registers in a context for the compiler's kernel thread, switch to the LS thread, to a complex scheme, which I'll describe a little bit later, will restore LS's kernel thread registers from the previously saved context from when LS last left off. Maybe LS will finish whatever system call it was executing, on the LS's kernel thread stack, and then return back to LS from the system call. And on the way to returning to user space, it'll restore these previously saved user registers for LS, and then resume executing LS. So there's a bunch of details here which we'll talk about, but maybe the main point here is that we never in xv6 see direct user-to-user context switches when we're switching from one process to another. Always the sort of strategy by which xv6 switches from executing one process to another process is you jump into the kernel, save the process state, run this process's kernel thread, switch to the kernel thread of another process that's suspended itself, and then return and restore user registers. So it's always this sort of indirect strategy. It's actually even more indirect than this, to thread switch, where the net effect is to switch from one user process to another user process. Questions about this diagram or anything?
The switch to the scheduler, that happens in between those two, right?
Yep. All right. Let me talk about the scheduler. So the real picture is actually significantly more complex than that. This is a more, going to be a more full diagram. Let's say we have process 1, which is executing, and process 2, which is runnable but not currently running. Now, the additional layer of details, we actually have multiple cores. In x86, let's say we have 2 cores. So that means that sort of at the hardware level, we have CPU 0, which is one of the cores, and let's say CPU 1. And the more full story about how we get from executing user space to, in one process, to executing in user spaces in another runnable but not yet running process. Now the first part's about the same as I talked about. I may say a timer interrupt forces transfer of control from the user process into the kernel. The trampoline code saves the user registers in the trap frame for process 1, and then executes user trap, which figures out what to do with this trap or interrupt. System call. Let's say it's a so for a little while we're executing ordinary kernel C code on the kernel stack of process 1. Let's say process 1, the kernel code for process 1 decides it wants to yield the CPU. It does a bunch of things, which we'll see the details of, that end up in a call to this routine switch, which is sort of one of the central routines in this story. Switch saves away this context, the registers for the kernel thread that's running in context 1. So there's 2 sets of registers, the user registers in the trap frame, the kernel thread registers in the context. Switch doesn't actually, switches from one thread to another, but in fact, the way x86 is designed, the only place that a user thread, the kernel thread running on a CPU can switch to is what's called the scheduler thread for that CPU. So we can't even switch directly to another process. We can only switch to the scheduler thread. So there's a, the complete thread apparatus dedicated to the scheduler for CPU 0. Since we're running on CPUs, this switch is going to switch to the previously saved registers for the scheduler thread. So let's say it's scheduler 0. And in the scheduler for CPU 0, switch will, by restoring these registers, since the registers include the stack pointer, the return from switch, as we'll see, will now actually return up to the scheduler function on CPU 0. And the scheduler function will do some cleanup to finish putting process 1 to sleep. Then it'll look in the process table for another process to run, a runnable process. And if it finds one, so we've sort of gone down here and up into the scheduler. If the scheduler finds another process to run, or even finds, if process 1 is runnable and still wants to run, it may find process 1 if nothing else wants to run. But in any case, the scheduler will call switch again to switch contexts to, say, process 2, in the process of which it'll save its own registers again in its own context. There'll be a previously saved context 2 from whenever process 2 left off. This set of registers will be restored. Process 2 will have made a previous call to switch to switch to the scheduler thread, just like process 1 did when it left off. That call to switch will return to whatever system call or interrupt process 2 was in. When that's finished, there will be a previously saved trap frame for process 2 that'll contain user registers. Those will be restored and will return back up into user space. And there's a separate scheduler thread for each CPU. So there'll also be saved context for the scheduler thread for CPU 1 and a scheduler loop running on scheduler 1. And whatever process, process 3 or something is running on CPU 1, when it decides to give up the CPU, it'll switch into the scheduler thread for its CPU. All right, there's a question, where are the contexts stored? It turns out that for the operations I've been talking about, the saved in fact, always for a thread switch, these contexts, these saved register sets for kernel threads are in the process structure. So any given kernel thread can only have one set of saved kernel registers because each thread is only executing at sort of a single place, and its context kind of reflects that place that it was executing when it left off, because a thread is a single thread of control. So a thread really only needs one context full of registers. So it's in the process structure. It's P arrow context. And the scheduler, each scheduler thread has its own context, which is actually not in the, there's no process associated with this scheduler thread. So there's actually, the scheduler's context is stored in the struct CPU for that core. There's an array of these CPU structs, one per core, each one has a context. Question, why can't we include the registers in the trap frame for the process? That is, actually those registers could be stored in the trap frame, which is made, because there's only one saved set of kernel thread registers per process. We could save them in any data structure for which there's one element of instance of that data structure per process. There's one struct proc per process, there's one struct trap frame per process. We could store the registers in the trap frame. But I mean, just sort of for maybe simplicity or clarity of code, the trap frame, I think, entirely consists of data that's needed when entering and leaving the kernel. And the struct context consists of the stuff that needs to be saved and restored when switching to and from between the kernel thread and the scheduler thread. Okay, question, is yield something that's called by the user or the kernel? It's called by the kernel. So the user threads, there's not really a direct way in XV6 for user threads to talk about yielding the CPU or switching. It's done by the kernel kind of transparently, at points in time when the kernel feels that it needs to happen. The threads, there's some times when you can sort of guess that probably a certain system call will result in a yield. Like if a process does a read on a pipe where it knows that really nothing is waiting to be read on that pipe, then the read will block. You can predict that the read will block and that the kernel will run some other process while we're waiting for data to appear in the pipe. And so the times when yield is called in the kernel, there's really two main times. One is if a timer interrupt goes off, the kernel always yields. Just on the theory that we should interleave the execution of all the processes that want to run on timer interrupt periods. So timer interrupt also always calls yield. And whenever a system call is waiting for IO, like waiting for you to type the next keystroke, does a read of the console and you haven't typed a key yet, then the machinery to wait for IO calls yield. It's called from sleep, something we'll talk about next week. All right. Okay,
sorry, can I ask another question?
Yes.
If it is asleep, is it gonna do the same thing roughly? So it's gonna be some system call, and then it's gonna save the trap frame, and then basically the same picture, but it's just that the thing that made the process go into the kernel was not a timer interrupt, but the process's own decision.
Yeah, so if the process does a read system call, and that's why it's in the kernel, and the read requires the process to wait for the disk to finish reading or to wait for data to appear in a pipe, then actually the diagram's exactly the same as this. Enter the kernel with a system call, a trap frame, hold the save user register will execute the system call. The system call will realize, I need to wait for the disk to finish reading something. The system call code will call sleep, which ends up calling switch, which saves away the kernel thread registers in the process context and switches to this current CPU scheduler to let some other thread run while this thread is waiting for the disk read to finish. So everything we're going to talk about now, except for the timer interrupt, is pretty much the same if what's going on is we're in a system call, and the system call needs to wait for I/O and give up the CPU. For the purposes of today's discussion, the two situations are almost identical. Okay, so the question, does each per CPU scheduler have its own stack? Yes, there's a stack for this scheduler and a stack for this, separate stack for the scheduler for CPU1. Yeah, and indeed, the stacks for the scheduler are just set up. In fact, all this stuff, you know, the context and the stacks for the scheduler threads are set up in a different way than for user processes. They're set up at boot time. If you poke around in start.s or start.c, start.s probably, you'll see some of the setup for each core's scheduler thread. There's a place where the stack, very early in the assembly code during boot, where the stack is set up for each CPU, and it's on that stack that the CPU boots on and then runs its scheduler thread. Okay. One piece of jargon, when people talk about context switch, they're talking about usually this act of switching from one thread to another by saving one set of register sets for the old thread and restoring previously saved registers for the thread we're switching to. So that's what's usually meant by context switch. Also, though sometimes it's applied to the complete dance that goes on when switching from one user process to another. And occasionally you'll see context switch applied to switching between user and kernel. But for us, we mostly mean it for switching from one kernel thread, typically to a scheduler thread. Just some pieces of information that are handy to keep in mind. Every core just does one thing at a time. Each core, you know, is just running one thread at any given time. It's either running some process's user thread, some process kernel thread, or that core's scheduler thread. So at any given time, the core is not doing multiple things, it's just doing one thing. And it's this switching that sort of creates the illusion of multiple threads running at different times on that core. Similarly, each thread is either running on exactly one core, or its state has been saved and we've switched away from it. So you know, a thread, just to be clear, a thread never runs on more than one core. A thread is either running on just one core, or it's not running at all. It has saved state somewhere. Another interesting thing about the XV6 setup is that these contexts that hold saved kernel thread registers, they're always produced by a call to switch. And so these contexts basically always refer to the state of the thread as it was executing inside a call to switch. And the way we'll see that come up is that when we switch from one thread to another and restore the target thread's context, the first thing it will do is return from a previous call to switch. So these contexts sort of always save state as it is in switch. Okay. Any more questions about the sort of diagram level situation?
I have a question. So
Yes.
we're using the term thread all the time, but it seems to me like our implementation for XV6, a process is only one thread. So like, could it be possible that one process could have multiple threads, or am I wrong here?
In XV6, all right, there's definitely some confusing things about the way we use the words here. In XV6, a process is either executing instructions at user level, or it's executing instructions in the kernel, or it's not executing at all, and its state has been saved away into this combination of a context and a trap frame. So that's the actual situation. Now, what you want to call that, well, you can call it what you like. I don't know of a simple explanation for this structure. We've been calling it, I've been saying that each process has two threads, a user level thread and a kernel level thread, and that the process, there's this restriction that a process is either executing in the kernel in the user space or executing in the kernel in an interrupt your system call, but never both. Yeah.
Okay, that makes sense. Thank you.
Yeah, I apologize for the kind of complexity of this. Okay, so let me switch to code, looking at the XV6 code. Right, so first of all, I just want to show some of the stuff we've been talking about. I'm going to look at the process structure. And we can see in the process structure a lot of the things we've been talking about. Just for review, there's the trap frame that saves the user level registers. There's a context here that saves the kernel thread registers when we switch to the scheduler thread. There's a pointer to this process's kernel stack, which is where function calls are saved while we're executing in the kernel. There's this state variable which records whether this process is running or runnable or sleeping or not allocated at all. And then finally, there's a lock that protects various things, as we'll see. For now, we can observe that it at least protects changes to the state variable, so that, for example, two scheduler threads don't try to grab a runnable process and run it at the same time. One of the many things this lock does is prevent that from happening. I'm going to run a simple demo program for you, this spin program. I'm using it mostly just to drive to sort of create the predictable situation in which we switch from one thread to another. But this program, spin program, creates two processes, and the processes both compute forever. Called fork here. I make a child, and then forever, both children just sit in this loop, and every once in a while they'll print a character just so we can see they're making progress. But they don't print characters very often, and they never sort of intentionally give up the CPU. So what we have here is essentially two compute-bound processes. And in order for both of them to run, I'm going to run them on a single CPU XV6 that has only one core. And so in order for both of them to execute, it's going to be necessary to do switching between the two processes. Let me fire up the spin program under GDB. Run the spin program, and you can see it's printing. One of the two processes prints // and the other prints // and you can see that every once in a while XV6 is switching between them. It only has one core the way I've configured it, so we see a bunch of forward slashes printing, and then apparently a timer interrupt must go off, switch the one CPU to the other process, and then prints the other kind of slash for a while. And so what I want to observe is the timer interrupt going off. So I'm going to put a breakpoint in trap, and in particular at line 207 in trap, which is the code in trap in devinter that recognizes that, we are in an interrupt, and the interrupt was caused by a timer interrupt. So I'm going to put a breakpoint here at trap.c line 207 and continue. And boom, the trap byte triggers right away because timer interrupts are pretty frequent. And we can tell from where that indeed we're in user trap, and user trap has called devinter to handle this interrupt. I'm going to type finish to get out of devinter and back into user trap. Because in fact, we don't, the code in devinter for timer interrupts does almost nothing. However, once we're back at in user trap, we can see that from this line here that we just returned from devinter. And the interesting thing about this is that what we're about to do, I mean, looking forward, we're currently at this line here, and we're looking forward to this call to yield. When devinter return 2, you can see from this value return is 2. The 2 is basically the device number, and we're going to see that by and by, because which device is 2, user trap is going to call yield, which will give up the CPU and allow it to switch to another process. So we'll see that in a moment. Meantime, let's look at what was currently executing when the interrupt happened. So I'm going to print P. The variable P holds a pointer to the current process's struct proc. Okay, we have a question. What makes each process's kernel thread different? Every process has a separate kernel thread. So there's really two things that differentiate different processes' kernel thread, because more than one could be executing on different cores. One is indeed that every process has a separate kernel stack, and that's what's pointed to by that k-stack element of struct proc. And the other is that early in, we're in user trap, which is the C code that's called by trampoline when an interrupt occurs. We can tell by this call that any kernel code can tell by calling myproc what the process is that's running on the current CPU. And that's another thing that differentiates, that allows kernel code to tell what process it's part of, that is, which process's kernel thread is executing. And what myproc does is basically use the TP register, which you may recall is set up to contain the current core's heart ID or core number. It uses that to index into an array of structures that say for each core, that the scheduler sets whenever it switches processes to indicate for each core which process is running on that core. So that's how different kernel threads are differentiated. Okay, so I was going to use that p-value, the name in that p-value to figure out what process is running. So XV6 remembers the name. It's that spin process, just exactly as expected. There were 2 of them, I think, with process IDs 3 and 4. Oops. We're currently executing in process ID 3. So after the switch, we'd expect to be in process ID 4, the other spin process. We can look at the saved user registers in the trap frame. And these are just the 32 registers that the trampoline code saves away to save the user state. Those are the user RA, return address register, user stack pointer, user program counter at hex 62. These are all familiar things from when we looked at traps. And maybe of the most interest is that the trap frame saves the user program counter, and it's at value 62. If we cared, we can look in the assembly code for spin.c, oops, which is spin.asm, and look for 62. Now we can see that, the timer interrupt occur during this add instruction in that infinite loop in spin. So it's not too surprising. Okay, so back to the trap code. Devin just returned. I'm going to type step a few times to get us to the to just being about to execute this yield. And yield is sort of the first step in the process of giving up the CPU, switching to the scheduler, letting the scheduler choose another kernel thread and process to run. All right, so let's actually step into yield. Now we're in yield. Yield's, if we have a question? No. Oops. Okay, we're in yield. Yield does just a couple of things. It acquires the lock for this process because it's about to make a bunch of changes to this process, and it doesn't want any other, and in fact, until it gives up the lock, the state of this process will be sort of inconsistent. Like, for example, yield is about to change the state of the process to runnable, which would, indicates that the process is not running but would like to. But this process is running, right? I mean, we're running the process right now. That's what's executing is the kernel thread for this process. And so one of the many things that acquiring this lock does is makes it so that even though we just changed the state to runnable, no other core's scheduling thread will look at this process and because of the lock and see that it's runnable and try to run it while we're still running it on this core, which would be a disaster, right? Running the same process on two different cores, and that process has only one stack. So that means like two different cores are, calling subroutines on the same stack, which is just a recipe for disaster. So we take the lock out. Yield changes the state to runnable. And what this means is that, when we finally given up the, when we finally yielded the CPU and given it up and switched to the scheduler process, this state will be left in this runnable state so that it will run again. Because after all, this was a timer interrupt that interrupted a running user level process that would like to continue computing. So we're going to leave it in state runnable so that it will run again as soon as the scheduler decides to. And then the only other thing the yield does is call this scheduler function. So I'm going to step into the scheduler function. I'll show this whole thing here. This scheduler function does almost nothing. It does a bunch of checks. It does a whole bunch of sanity checks and panics. And the reason for that is actually that this code in XV6 over its many-year lifetime has been among the most bug-prone and had the most surprises, unhappy surprises. And so there's a lot of sanity checks and panics here because there's often been bugs associated with this code. All right, I'm gonna skip over these sanity checks and proceed to the call to switch. This call to switch is where the real action happens. This call to switch is gonna save away the current kernel threads registers in PRO context, which is the current process's saved kernel thread context, saved set of registers. C arrow context, C is the pointer to this core's struct CPU. And struct CPU has the context, the save registers of this core's scheduler thread. So we're going to be switching from this thread and saving this thread state, restoring the thread state of this core's scheduler and sort of continuing the execution of this core's scheduler thread. Okay, so let's see what, let's take a quick preview at the context that we're going to be switching to. And I can get that. Turns out that I can't actually print C arrow context, but I happen to know that C prints to CPU's 0, just because we're on the 0th core. There's only one core, and I can print its context. And so this is the saved registers from this core's scheduler thread. And of particular interest is the RA, because the RA register is where the current function call is going to return to. So we're going to switch to the scheduler thread, and it's going to do a return and return to that RA. And we can find out where that return address is by looking in kernel.asm. Actually, that's and as you can see, this x/i prints the instructions that are at a certain address, but it also prints the label of the name of the function that those instructions are in it. So we're going to be returning to scheduler by and by. That's just, as you might expect. Okay. I want to look at what switch actually does. We're about to call switch. So I'm going to put a breakpoint on switch. I'm putting a breakpoint because there's a bunch of setup code like that pulls the values of context out of those structures. I'm going to skip over it. Okay, so now we're at a breakpoint in switch. The GDB won't show us the instructions, but we can look in switch.s to look at the instructions we're about to execute. So as you can see, we're on the very first instruction, the store of RA to the address pointed to by A0. You may remember in the call to switch that the first argument was the current thread's context, and the second argument was the context of the thread we're switching to. The two arguments go in A0 and A1. And so the reason why we see all these stores through register A0 is because we're storing away a bunch of registers in the memory that A0 points to, that is in the context of the thread we're switching from. And the loads load from address A1 because that's a pointer to the context of the thread we're switching to. Okay. And so thread, switch saves registers, loads registers from the target thread's context, and then return. And so that's why the RA was interesting, because it's going to return to the place that RA pointed to, namely into scheduler. All right, so one question is, you may notice here that while switch saves RA, SP, and a bunch of S registers, one thing it does not save is the program counter. There's no mention of the program counter here. So why is that?
Is it because the program counter is updated with like the function calls anyway?
Yeah, it's the program counter. There's no actual information value in the program counter. We know that where we're executing right now is in switch, right? So there'd be no point in saving the program counter because it has an extremely predictable value, namely this instruction, the address of this instruction in switch. What we really care about is where we were called from. Because when we switch back to this thread, we want to continue executing at whatever point switch was called from. And it's RA that holds the address of the instruction that switch was called from. So it's RA that's being saved away here. And RA is the point at which we'll be executing at again when switch returns. So we can even print that. We can print RA, whoops. We can print RA, and we haven't actually switched threads yet. You remember we came here from the sched function. So RA is, as you might expect, a pointer back into the sched function. Another question is, how come switch only saves 14 registers? I counted them. It only saves and restores 14 registers, even though the RISC-V has 32 registers available for the for code to use. Why? Why only half the registers are saved?
Well, when switch was called, it was called as a normal function. So whoever called switch already assumed, well, switch might modify those. So that function already saved that. on its stack, meaning that like when we jump from one to the other, that one's gonna self-restore its caller saved registers.
That's exactly right. The switch is called from C code. We know that the C compiler saves on the current stack any caller saved registers that have values in them that the compiler is going to need later. And those caller saved registers actually include, I think there's 18, depending on how you count them, there's somewhere between 15 and 18 caller saved registers. And so the registers we see here are all the registers that aren't caller saved and that the compiler doesn't promise to save, but nevertheless may hold values that are needed by the calling function. So we only have to save the callee saved registers when we're switching threads. Okay. Final thing I want to print is we do save and restore the stack pointer. The current stack pointer, it's like hard to tell from this value what that means, but it's the kernel stack of the current process, which I don't know if you recall, but is allocated, is mapped by the virtual memory system at high memory. Okay, so we're going to save away the current registers and restore registers from the scheduler threads context. I don't want to like execute every single one of these loads and stores, so I'm going to step over all the 14 loads, the 14 stores and the 14 loads. Going to proceed directly to the return instructions. Okay, so we executed everything in switch except the return. Before we do the return, we'll just print the interesting registers again to see where we are. So stack pointer now has a different value. The stack pointer now points into this stack 0 area in memory. And this is actually the place very, very early in the boot sequence where start.s puts the stack so it can call the very first C function. So actually back on the original boot stack for this CPU, which just happens to be where the scheduler runs. Okay, the program counter, not very interesting. We're in switch because we haven't returned yet. And the RA register now points to scheduler because we've loaded, we've restored the register set previously saved by the scheduler thread. And indeed, we're really now in the scheduler thread. If I run where, the where now looks totally different from the last time we ran it. We're now indeed in a call to switch, but now we're in a call from switch to switch that the scheduler made at some point in the past. And the scheduler was run long ago during boot, was called as the last thing that main did during the boot process. So I'm going to execute one instruction to return from switch now into scheduler. So now we're in this course scheduler. Let's look at the full code. So this is the scheduler code. This function called scheduler. And now we're executing in the scheduler thread for the CPU. And we're just at the point, we've just returned from a previous call to switch that the scheduler made a while ago when it decided it was going to start running that process, PID3, which was the spin process that was interrupted. So it's this switch, process ID 3, that spin called switch, but it's not that switch that's returning. That switch hasn't returned yet. It's still saved away in process IDs 3's stack and context. We just returned from this earlier call to switch. All right, so the stuff that happens here in the scheduler, we're stopped running this process, and so we want to forget about the various things we did in the process of running this process. We want to forget the C arrow proc equals 0. Basically means that we're forgetting that we're no longer running this process in this core, so we don't want to have anybody be confused about that. And we set this per core proc pointer to 0 instead of this process. The next thing that happens is that you remember yield acquired the lock for this process because it didn't want any other core scheduler to look at this process and maybe run it until the process was completely put to sleep. We've now completed the switch away from this process. And so we can release the lock on the process that just yielded. That's the release. And at this point, we're still in the scheduler. If there was another core, at this point, some other core scheduler could find that process because it's runnable and run it. But that's okay because we've completely saved its registers. We're no longer executing on that process's stack because we're now executing on this core scheduler stack. So it's actually fine if some other core decides to run that process. Okay, but there is no other core, so that doesn't actually happen in this demonstration. I actually want to spend a moment talking about the PRO lock a little bit more. PRO lock actually does a couple of things. It does really two things from the point of view of scheduling. One is that yielding the CPU involves multiple steps. We have to set the state to run up, change the state from running to runnable. We need to save the registers in the yielding processes context, and we have to stop using the yielding processes stack. There's at least 3 steps, which take time in order to do all the steps required to yield the CPU. And so one of the things that lock does, as I mentioned, is prevent any other core scheduler from looking at our process until all 3 steps have completed. So the lock is basically making those steps atomic. They either all happen from the point of view of other cores or none of them have happened. It's going to turn out also when we start running a process that the PRO lock is going to have a sort of similar protective function. We're going to set the state of a process to running when we start executing a process, and we're going to move its registers from its process context into the RISC-V registers. But if an interrupt should happen in the middle of that process, the interrupt's going to see the process in a weird state, like maybe in the state of marked running, but hasn't yet finished moving its registers from the context into the RISC-V registers. And so that would be a disaster if a timer interrupt happened then, because we might switch away from that process before it had restored its registers. And switching away from that process would save now uninitialized RISC-V registers into the process's context, overwriting its real registers. So indeed, we want starting a process to also be effectively atomic. And in this case, holding PRO lock across switching to a process, as well as preventing other cores from looking at that process, also turns off interrupts for the duration of firing up, of switching to that thread, which prevents a timer interrupt from ever seeing a process that's only midway through being switched to. Okay. So we're in the scheduler. We're executing this loop in the scheduler. There's this loop in the scheduler that looks at all the processes in turn to find one to run. And in this case, we know there's another process because there's that other spin process that we forked. But there's a lot of process lots to examine. So I want to skip over the actual the scanning of the process table and go direct to the point at which the scheduler finds the next process. So I'm going to put a breakpoint at line 474 where it's actually found a new process to run. So boom, here we are. The scheduler has scanned the process table and found another process to run. It's going to cause that process to run. You can see at line 468 it acquired that process's lock. So now it's entitled to do the various steps that are required to switch to that process. In line 473, it set the process's state to running. It's now at 474 going to record in the CPU structure which process the CPU is executing, and then call switch to save the scheduler's registers and restore the target processor's registers. So we can see what process it found by looking at the new process's name. And surprisingly, it's spin. Its process ID is now 4. It used to be running 3, now running 4. And we've already set the state to running, so just the state's running. We can see where this thread is going to switch to in the call to switch at line 475. print this context, these saved registers. So where is the RA? Of course, we're going to call switch, but switch, as we know, returns. When it returns to the restored RA. So what we really care about is where is it that RA points to. We can find that out by using x/i. It's going to return RA points to some point in SCED. So that's not too surprising, since presumably that other spin process was suspended due to a timer interrupt, which, as we know, calls SCED, which calls switch. All right. So we're about to call switch. Let me just bring up the switch code again. Actually, enter switch, we're still, where shows that we're still in the scheduler's context. I want to, again, execute all of the instructions with switch, this time switching from the scheduler to the new process. So we skip over the 28 stores and loads. Just convince ourselves that we are actually about to return to SCED. So now, since we're about to return to SCED and not scheduler, we must now be in a process's kernel thread and no longer in the scheduler thread. And indeed, if we look at the backtrace, we had a user trap call that must have been a timer interrupt from sometime in the past that, as we've seen, called yield and SCED, but it was a timer interrupt in the other process now, not in the process that we originally looked at. Okay, any questions about, I think I'm gonna leave off stepping through the code at this point, and any questions about the any of the material we've seen?
Oh, sorry. If it was, for example, a disk IO, then we would see that our array would point somewhere to like sleep or something like that, right?
Yes. Well, we'd see the where at this point would include some system call implementation functions and a call to sleep. As it happens, I think, I mean, this is you're basically, the answer to your question is yes. If we had just left off executing this process for some reason other than timer interrupt, switch would be basically returning to some system call code instead of to SCED. As it happens, I think sleep may call SCED. So the backtrace would look different. It would just happen to include SCED, but yes. So I've chosen just one way of, just one way of switching between processes due to timer interrupts. But you also get switches to wait for user IO or to wait for other processes to do things like write to a pipe. Okay, one thing you probably noticed is that scheduler called switch, and we're about to return from switch here, but we're returning really from a different call to switch than the one the scheduler made. We're returning from a call to switch that this process made a long time ago. So, this is potentially a little bit confusing, but this is how the guts of a thread switch work. Another thing to notice is that the code we're looking at, this switch code, this is really the heart of thread switching. And really all you have to do to switch threads is save registers and restore registers. Now threads have a lot more state than just registers. They have variables and stuff in the heap and who knows what, but all that other state is in memory and isn't going to be disturbed. We haven't done nothing to disturb any of these threads stacks, for example, or heap values. So the registers in the microprocessor are really the only kind of volatile state that actually needs to be saved and restored to do a thread switch. All the stuff's in memory. The stack, for example, will still be in memory undisturbed. And so it doesn't have to be explicitly saved and restored. Now we're only saving and restoring this microprocessor, the CPU registers, because we want to reuse those very registers in the CPU for the new thread and overwrite whatever values they have. So the register, that's why we have to save the old thread's registers.
What about other processor state? So I don't know if the RISC-V processor that we're using has other flags, but I know like some x86 Intel chips have like the floating point unit state and like things like that. Do we just not have that in RISC-V?
Absolutely.
Like in our version?
Your point's very well taken. On other microprocessors like x86, the details of switching are a bit different because they had different registers in different state. And so the code, this is very, very RISC-V dependent code, and the switch routine for some other processor might look quite different, might have to save floating point registers. RISC-V actually uses the general purpose registers. Actually, I'm not sure what it does for floating point, but the kernel doesn't use floating point, so it doesn't have to worry about it. But yeah, this is totally microprocessor dependent.
A question about the timer interrupts. So it sounds like the core of all of the scheduling working is that there will be a timer interrupt. What happens in cases where that malfunctions?
There is going to be a timer interrupt. So the reasoning for how come preemptive scheduling of user processes works is that user processes execute with interrupts turned on always. x86 just ensures that interrupts are enabled before returning to user space. And that means that a timer interrupt can happen if you're executing in user space. So there's nothing a user process, if we're in user space, the timer interrupt just will happen when the time comes. It's a little trickier in the kernel. The kernel sometimes turns off interrupts. Like when you acquire a lock, the interrupts are going to be turned off until you release it. So, so if there were some bug in the kernel, if the kernel turned off interrupts and never turned them back on, and the code in the kernel never gave up the CPU, never called sleep or gave up the CPU for any other reason, then indeed a timer interrupt wouldn't occur, and that would mean that this kernel code may, would never give the CPU. But in fact, as far as we know, we wrote XV6 so that it always turns interrupts back on. Or, if there's code in XV6 that turns off interrupts, it either turns them back on, and so a timer interrupt can then occur in the kernel, and we can switch away from this kernel thread, or the code returns back to user space. Kernel code returns back to user space. We believe there's never a situation in which kernel code will simply loop with interrupts turned off forever.
I got it. My question was more about so I assume the interrupts are actually coming from some piece of hardware. What if that piece of hardware malfunctions?
No. Then your computer's broken and you should buy a new one.
Okay.
That's a valid question there's, 10 billion transistors in your computer, and indeed, sometimes the hardware just has bugs in it, but that's beyond our reach if you add 1 and 1 and the computer says 3, then you just have deep problems that XV6 can't help you with. So we're assuming that the computer works. The only time when software, there are times when software tries to compensate for hardware level errors. Like if you're sending packets across a network, you always send a checksum so that if the network hardware, flips a bit, malfunctions and flips a bit, then you can correct that. But for stuff inside the computer, that people tend not to, it's just, people basically don't try to make the software compensate for hardware errors.
Oh, I have a question. Why? In trampoline.sn in Switch, we write the code in assembly. Is that why? Is that because we want to make sure that exactly these things happen? So you cannot write it in C because we just need those exact things to happen, basically.
Yeah, certainly we want this exact sequence to happen. In C, it's very hard to talk about things like RA in C or SP. Certainly there's no way within the C language to talk about changing the stack pointer or the RA register. So these are things that just can't be, you can't say it in ordinary C. The only way you can say it in C is it's possible in C to sort of embed assembly instructions in the C code. And so we could have just embedded these assembly instructions in a C function, but it would amount to the same thing. We're basically operating at a level below C, so we can't really use C here.
I have a question about when a thread finishes executing. I'm assuming that happens in the user space when we call the exit system call, and that also ends the process, the thread, I'm assuming, in the kernel space. But if the thread ends before a new time interrupt happens, does it still is this like the CPU still acquired by that thread, or do we end that thread and start a new one before the new time interrupt?
Oh yeah, the thread yields the CPU. The exit yields the CPU. So there's actually many points. Even though I've been driving this discussion with the timer interrupt, in fact, in almost all cases where XV6 switches between threads, it's not due to timer interrupts. It's because some system call is waiting for something or decides that it needs to give up the CPU. And so, for example, exit does various things and then calls yield to give up the CPU, and it does that. There's really nothing, it does that independently of whether there's a timer interrupt. Yes. All right, the time is up for this lecture. I think I'll continue some of this discussion next week, but I'm happy to take more questions right now if people have them.
So let's say the operating system actually takes on the thread implementation. So for example, you want to run multiple threads of a process on multiple CPUs. Like that has to be handled by the OS. That cannot just be handled in user space, right? How does that kind of switching work? Is each thread now becomes the same as the processor? It's like, is the OS going to loop through all existing threads? Or, because like each CPU will still switch between, even if one process has give me 8 cores, like it's still going to switch each of the CPUs between those and then a couple of other processes. And then also we don't want to really switch like between one and the other thread on the same CPU, or do we? I don't know.
Wait, I'm not sure what the question is.
Yeah, I guess can you just explain more, like how does that happen?
How does what happen?
Let's say we have multiple threads per process so that they can run on different GPUs.
Yeah,
like
so
how do we go about there?
Yeah, so Linux, for example, supports multiple threads per process. And in Linux, the implementation, it's a complex implementation, but maybe the simplest way to explain it is that it's almost as if each thread in Linux is a complete process. And the threads of a given, what we would call the threads of a particular process, are essentially separate processes that share the same memory. So Linux has sort of separated out the notion of thread of execution from address space, and you can have them separately. And if you make 2 threads in one process, it basically makes 2 processes that share one address space. And then from then on, the scheduling is not unlike what XV6 does for individual processes.
I see. And then is there anything like, does the user have to specify like, okay, pin each thread to a CPU? Or how does the OS make sure that different threads of the same process don't run on the same core? Because that's kind of defeating the purpose, or not, I guess. I don't know.
It's actually just like, it's much like XV6, namely there's 4 cores, and Linux will just find 4 things to run on those 4 cores. They may be, if there's not much going on, then maybe there'll be 4 threads of the same process. Or if there's 100 users logged in on an Athena machine, maybe it's one thread each from multiple different processes. You know, there's not any one answer. You know, or the kernel basically finds something for each core to do, and then that core does that thing.
Okay, that makes sense.
Yeah. You can, you know, if you want to do careful measurements, there is a way to pin threads to cores, but people only do it when they're up to something strange.
So
And
they
then-
share the same virtual table,
Can you say it again?
virtual memory. So they say they have the same page table, those threads.
Yeah. If you're on Linux, if you create 2 threads in one process, then you have these 2 threads that, I don't know if they like literally share the exact same page table or whether their page tables are identical, one or the other.
Is there a reason why they would have to be separate ever? If you manually map memory, or?
I don't know enough to know whether
Mhm.
which Linux does.
Okay, I have another question about like a small detail. So basically, like from my understanding, when you call switch, you switch from one call to switch to another. So the first time you call switch, you have to like kind of artificially create that other endpoint to come back to, right?
Yes.
Because you can't just randomly jump into any code.
Yes. You want to know where that context is cooked up.
Probably somewhere where the process is created, I guess. I don't know.
Yeah. Maybe user init or let's see, not user init, alloc proc. No, alloc proc.
There's something called fork trap or something.
Yeah, look at this. Yeah. Well, yeah, fork ret. Okay, so in alloc proc, which is called both for the very first process at boot time and by fork, alloc proc sets up the critical elements of the context for the new processes. It sets up the new processes context. It actually doesn't matter what most of the registers are, but it does matter what RA is, because that's where the switch, the very first switch in that process is going to return to RA. And that process is going to need to use its own stack. So RA and SP are set up or faked, essentially, so that the very first switch into a process works.
So if I understand this correctly, like when the switch will happen, then it'll basically just start executing the first instruction inside of the fork red as if
Yes.
fork red just called switch and returned from it.
Yeah. The return from switch is going to be a jump to the beginning of fork ret.
Right.
Yeah.
Interesting. Do we ever call fork red, or is it always happen?
I don't
Like
think
it
fork
always
ret-
happens like this.
Yeah, I don't think anything ever calls fork ret for real. I think it's just, yeah, it's only executed in this weird way from first time a process is run. And it's really its job is to release the lock that the scheduler took
Mhm.
and then return. And then this user trap ret, of course, is also fake in that it's it's like
Jump.
it's as if returning from a trap, except the trap frame is faked also to have to like jump to the first instruction in the user
Right.
code.
Oh, but the trap frame, it's again the same. Like you don't need to initialize any registers because it's like, well, we're going to the beginning, so
Except for
you
the-
don't need to assume anything.
Yeah, the program counter I think is
Yep.
it needs to be initialized to 0. I don't know what else. Yeah, maybe it.
I mean,
Maybe
probably
if-
if we call them, it doesn't, right? Because if we already do the call, then that's going to set the program counter.
Yeah. So here's this only happens. Oh, because fork
Oh.
copies the program counter, the user program counter.
Mhm.
And so the only time when we're not doing a fork is for the very first process where it's like explicitly set to 0.
Oh,
And stack pointer
Oh,
apparently
yeah.
also needs to be set up.
oh yeah, because that's EPC. That's not PC. That's the one that's going to get swapped by the trampoline.
Yes.
Oh, I see. Because the real PC is actually going to be in inside trampoline, but then we're going to switch it to jump to there.
Yeah.
Interesting. Can I just ask, like, can you go back to the alloc proc? I think there's oh no, sorry, forkret. There's something there that happens, I think, for the first process only. What's this for if first call? I wasn't really sure what happened
Well,
here.
let's see, the file system, the file system needs to be initialized, and in particular, some stuff needs to be read off the disk in order to get the file system going. Like there's this thing called the super block, which describes like how big the file system is and where the various things are in the file system. And there's also a crash recovery log that needs to be replayed in order to sort of recover from a previous crash if there was one. But in order to do anything in the file system, you need to be able to wait for disk operations to complete. But the way XV6 works, you really can only execute the file system code in the context of a process in order to like wait for IO. And so therefore the initialization of the file system has to be deferred until the first time we have a process running. And that occurs in the very first process in forkret.
I see. And I'm guessing we'll learn more about this later.
Yeah, not about this horrible
In the
hack,
semester.
but about how file systems work.
All right. Okay. Well, thank you. I'm sorry for holding on to
Oh, no.
so long.
Sorry, is
Thanks
that
for
the
all the answers.
process? Oh. Sorry,
ahead.
is that going to be the init process when this thing is executed?